All right, so we'll work through these. So number 17. So we're told 40% of credit card customers carry a balance from month to month. Suppose we interview 10 credit card customers. What would be the expected number, right? Or the mean number of customers who carry a credit card balance? Now, here's where, if I'm asking for the expected value and I've got a setup like this, where I either see someone carry a balance or I don't, so success, failure, I'm interested in the number of successes or the number of people who carry a balance out of 10, right? Out of some cap number, right? Some maximum number. This is going to be a good example where we can use that binomial distribution. And like I said, notice the practice exams, they follow kind of a similar pattern, right? A similar, we kind of go through things from in the order we went through in class. So the binomial stuff kind of coming here at the end. So I look at my formula sheet. Here's my binomial equations. I've got my mean, my variance, my standard deviation, and then I have my probability mass function. So the mean, right, another word for that we said when it comes to these random variables is my expected value. So let me see if I can, well, kind of out of whack here. Go out just a little bit, there we go. So I had 10 people, so my N was 10. The probability any one person carried a balance was 40%, so that probability would be 0.4. So if I want to find the mean, or what we sometimes reference as the expected value of this random variable x, it's simply n times p. So what? 10 times 0.4 gives me that expected value of 4. Should be a relatively easy question, right? Another one where you can get some kind of easy points there. All right. I want to find the variance. Well, that's just n times p times 1 minus p. Right? Just kind of jotting that down from the formula sheet. So for us, 10 was my n times 0.4 times 1 minus 0.4, and should get 2.4 there for the variance. Right? So sometimes I'll combine problems like this, where maybe I'll ask you for the mean and the variance of a binomial distribution all in the same problem. But once we've identified this is a setup for a binomial distribution, we can always just use those equations from the formula sheet for the mean and the variance. Okay. Any questions on that? We'll keep moving.
The first one was expected number.
Yep. So we can kind of think about this as the expected value or the mean of the, or sorry, the expected value or the mean of this binomial distribution, right? Or this binomial discrete random variable. Okay. So that would kind of get 17 and 18, right? 19 is what's the probability exactly 4 customers carry a balance? Well, first of all, which of these can I rule out right away? Fine. So if I want a probability, the very first thing I should think about is what's it bounded by? 0 and 1. So 1.2 doesn't make any sense. Now from there, if I think a little bit harder about this one, like let's say I try using the formula, which we've got right here, that probability mass function, the probability that x is equal to 4. I can't get to work. I don't know, my calculator, something's going wrong. I'm panicking. Well, I've already ruled out C. If I think about here, I've already got the expected number or the mean, this binomial distribution. So I know that 4 is going to be the most likely outcome. It's my expected value or my mean. And we know that 4 is going to be the most likely outcome. And then, you know, everything as we move further from that, the probabilities are going to decline, right? So if 4 is the most likely outcome, I would find it kind of hard to believe that the most likely outcome only has a probability as high as 0.07. So I'm probably, you know, can rule out D there, right? I mean, I guess theoretically, I can't. I mean, it could be. It is a positive probability, but it seems too small. So if I'm just guessing here, taking a guess at this, I'm probably going to go with A or B. Another thing to remember is that with these binomial distribution examples, like relatively high probabilities of seeing one specific outcome are usually like 0.2 or 0.3. So 0.7 seems very, very high. If you think about it this way, like I've got 10 people, right? On average, 4 of them carry a balance. So, I mean, you know, just because the mean is 4, that's the most likely outcome, 3 or 5 wouldn't be that unlikely for me to see if I'm just grabbing 10 random people. So to have a probability as high as almost 0.8, right? 0.77 associated with one outcome. Well, think of all the other, you know, possible outcomes I could see here. Yeah, the probabilities are declining, but I'm not that, whoops, not 4. I'm not that far away from the mean. So 0.77 even seems too high. If I'm guessing here, probably going to go with B, right? The most likely outcomes usually have a probability of 0.2, 0.3, maybe a little bit lower than 0.2, but not you know, not much below that. Right? Yeah, so now if I actually want to calculate it, right, I'm going to use this equation here. So I can, you know, use my intuition to kind of rule things out, but it's probably best practice to actually try to solve it, right? But I'm just saying in case we got stuck, we can kind of think about more broadly, not get too lost in the formula. So I'm going to just write the formula out. So n factorial, my x was 4, n minus x factorial, probability of success was 0.4 to the x times 1 minus 0.4 to the n minus x, so 10 minus 4 there. So I just wrote out that formula, plugged in the values that we had for n, p, and then the x value we were interested in was finding the probability x is exactly equal to 4. Now, you can put this in your calculator all in one line. Hopefully you've found those factorial buttons at this point. But if you didn't, right, you can kind of break this down into parts, right? So maybe the first thing I do is do the math I can do in my head, right? So this is just going to be 0.6 to the 6th, so I can get rid of some of those parentheses. So here, I'm going to break this down into 2 parts, and I'm going to cheat. And I don't think this will be in the video, so. Did I get this entered right? So 0.00119. So if I break this part down, so just 0.4 to the 4th times 0.6 to the 6th, this was 0.001194. And then I'm going to break this component down as well, right? So I could get this entered into my calculator. I didn't have 2 things, right? It makes it a little bit easier. I would then only have 2 numbers I have to multiply. Now, I could put this all into my calculator. That's fine, like using the factorials. Or if I write this out, what I'll notice is 10 times 9 times 8 times 7 times 6 times 5, etc. over 4 times 3 times 2 times 1. And then 10 minus 4 would just be 6. So times 6 factorial. We'll notice everything past 6 would cancel. And all I have is 10 times 9 times 8 times 7 divided by 4 times 3 times 2 times 1. I think if I remember right, if I get that entered into my calculator, that's just 210. And now I've got kind of, right, I broke it down into 2 parts and I have to multiply this. Now I can do it all on one line in my calculator if I want, but sometimes it makes it easier to kind of break it down there. Okay. Any questions over anything I did there? Yeah, I think it's I think if you actually, yeah, as I say, if you round to the 3rd decimal, it should be about 0.251, I think. Any questions over any kind of step or the procedure there? And, you know, sometimes I might do something on the exam where I ask you for a relatively high number of occurrences, and writing it out kind of makes it a lot easier. Imagine if I had something like 40 factorial over 2 factorial, something like this. Well, I mean, this simplifies down to 40 times 39 times 38, etc. 2 times 1, and then 38 factorial. So everything past 38 would cancel, and this simplifies to be something quite a bit easier. But that's how you would use that binomial to find the probability of exactly one number of successes. Any questions on that before we keep moving? Okay. The next question I believe is what's the probability that at least one customer carries a balance? Right. So now we want to find the probability that at least one person carries a balance. So what we're really saying there is, what's the probability X is greater than or equal to 1? Now, generally, we can look at something like this and say, okay, I either see exactly one person carry a balance, I see exactly 2, exactly 3. So these are all mutually exclusive. I'm only going to see one of these outcomes. So I can just add up the probability of every possible outcome that fits this criteria. Okay. So the probability that X is equal to 1 plus the probability X is equal to 2, all the way up to the probability X is equal to 10. Well, man, I got 50 minutes to take this exam. I got to use that binomial function 10 different times. This doesn't seem very, doesn't seem very fair, right? Well, that's probably because there's another rule we can use to make this a lot easier, right? So anytime you're dealing with this binomial or a Poisson example, and you've got something that looks like this, think about maybe how you could rewrite your probability. So if this is event A, we said the probability of A is always going to be equal to 1 minus the probability of its complement. So if A is that X is greater than or equal to 1, what would A complement be? So it's just the exact opposite of that, or everything that's not in event A. Yeah, so X is less than 1. Now, from here, we have a discrete variable. So what's the only outcomes that fit this criteria? Yep, and I think I said outcomes, but right, it's the only outcome, right? There's only one of them, okay? So now, I just have to find the probability that X is equal to 0. So n factorial, so n was 10 over X factorial, n minus X factorial. Probability of success is 0.4 to the X times 1 minus that probability of success to the n minus X. So once again, I was just using that binomial formula. I'm doing it from memory, but you'll have it there in front of you, plugging in my values for n, X, and P. Okay. Well, now notice here, and also this was just for the probability, so I am, whatever that ends up being, I still need to subtract it from 1. Well, I can simplify this down quite a bit. 10 factorial over 10 factorial cancels. 0 factorial is 1. This entire fraction here is 1. 0.4 to the 0 power, anything to the 0 power is 1. So really all I'm left with is this guy over here. So 1 minus 0.6 to the 10th. All right, so things would simplify down quite a bit there. I wouldn't have to like enter that whole thing into my calculator, maybe making a mistake. So I don't know, this is like 0.99 something, right? This is a very small number. Okay. Any questions on that? Where are we at in time? Okay. But I wanted to point something out here. Like, let's say I got lost in the formula and I don't know, something wasn't making sense, or I forgot to subtract it from 1 and I got a really small value. Going into this one, I should have thought about this ahead of time. I wanted the probability that X is greater than or equal to 1, right? That would mean take the probability X is equal to 1, add to that the probability X is equal to 2, plus 3, plus 4. If I added up all these probabilities, that's every possible outcome except for 0. Also, it includes the most likely outcome and values that are right on either side of the most. So this is going to be a very high probability. So right away, I should be thinking this is going to be a relatively, like, pretty high probability, probably close to 1. It's adding up the probability of every possible outcome other than 0. So when I'm looking at these possible answers, A or C are really going to be the only ones that make sense. Okay? I mean, something that's going to be pretty close to 1, right? The things that are 0.9 are going to be really the answers that make any sense in this one. And that's just taking a step back, not getting lost in the formulas, and just think about what I'm trying to find the probability of. Right? If on average 4 people carry a balance, and I want to know what's the probability that 1 or more, well, that's, I mean, the only other outcome that doesn't fit that criteria is that 0 people carry a balance, right? And that seems like it, should be a relatively low probability because it's pretty far from that mean of 4, right? which means that the probability of being greater than or equal to 1 should be a relatively high probability. Yep.
I remember I kind of got lost. We still do the 1 minus the outcome of that 10 factorial over 4 factorial.
Yeah, so
Okay, so I'm
yep, so this was originally what we were looking for. So 1 minus the complement, and from there it's just I'm rewriting, right? That's the only outcome that's less than 1, writing out that probability using my probability mass function, but yeah, I still have to subtract that from 1. Yep. Exactly. Yep. Any other questions? All right, so one thing that's not on practice exam B, and there is a question at the end of practice exam A, looking at the Poisson. And I know that we did it last class on Monday, but I want to reiterate, wink, wink, that you should know how to do this. Okay. So let's say that I've got, I don't know, I get 12 emails an hour or something like that. Okay? And I then ask you, okay, well, what's the probability that over the next minute, I get 1 email? Right? Is this clear so far?
Yeah, I just didn't know if it's a certain number.
Oh, no. So this is, I'm adding this in, which means there's probably a reason why I'm adding it in. So I've got my mean over an hour, but I'm interested in finding the probability of seeing a certain number of successes in a minute. I've got a time interval. I'm thinking about number of successes. This is a good example of the Poisson distribution. So if I ever have an example like this where, bless you, my mean doesn't match up with the time interval I'm interested in finding the probability of a certain number of successes in, I need to find what my average would be in my new time interval, right? So if there's 12 every hour, how many would there be in a minute? Well, I'll take that old lambda. I'm going from a larger to a smaller time interval. So I want to make my new mean should be smaller, right? If I get 12 emails an hour, every minute I'm going to get something less than 12. So I need to be dividing that old average that I have by some factor. Okay. So that was whenever we were going from a larger to a smaller interval, we divide by a factor. The reverse, if we ever wanted to go from a smaller to a larger interval, well, that's where we multiply by some factor, right? We need to kind of make that new mean a little bit higher. So here I've got 12. What should I be dividing by? I'm going from hours to minutes. Not 120, right? How many minutes would there be in an hour? That's all we need, right? So you don't worry about like multiplying or think about how many minutes or 60 minutes. I've got 12 here. It's just how many minutes are in an hour, right? Kind of like I think the examples we did Monday were how many months in a year, how many days in a week. Yeah.
What's that symbol?
This guy?
Yeah.
This is lambda. So this is just a way that we indicate the Poisson's average rate, right? So I don't know. Maybe I'm not drawing it very well. Let me see. I'll show it to you on the formula sheet. It looks more like this, right? So I guess mine kind of looks screwy, but that this is what it is. So, but yeah, that's just the average rate, and that's something we have to be given with these Poisson examples. Like I would have had to give you that the average rate over an hour is 12. So here's my kind of average rate. Now if I get 12 emails an hour, on average, I'm going to get what this is 1/5 every minute, one fifth of an email every minute. So I now can use my Poisson distribution equation, which is down here, right? So my lambda now, or that average rate, is 1/5. So lambda to the x, my x here, kind of making this easy, is just 1, times e, that natural number, to the negative lambda, which is 1/5, and then over x factorial. All right. And then that, get that entered in my calculator, and the answer is whatever it is. I don't know what it's off the top of my head, so it's gonna be what? 1/5 times e to the negative 1/5. So what? 0.2 is 1/5. So times e to the 0.2, no, negative 0.2. So if you get that entered in your calculator correctly, it should be about 0.16. Any questions on this one? So, right, the original average we were given was 12 an hour. Because I was trying to find the probability of a certain number of successes in a minute, I had to come up with the average rate per minute. So if I know the average rate over an hour is 12, the average rate over a minute would just be 12 over 60, right? Because there's 60 minutes in an hour. And then that's my kind of average rate every minute, or my lambda. Does that answer? Is it? Okay. So originally, this is all I had, right? I know that every hour I get 12 emails. I'm then asked for what's the probability over this next minute that I get exactly one email. Well, I don't know how many emails I get on average every minute, but if I know how many I get every hour, then every minute I should get just that many divided by 60, because there's 60 minutes in an hour, right? So I take that old average or the old time period or time interval I had, divide it by that factor of 60, which I'm going from hour to a minute here. If I was going from year to a month, I divide by 12, week to a day, divide by 7. And that's where that new kind of average rate over that minute, the time interval I was interested in, that's where that lambda came. Is that okay? Yeah. So like think about it this way. If I know on average over a year, I don't know, let's say something like, make it easy, 24 my students fail my class. I don't think it's that high, but let's say it is, right? Then in every month, on average, how many people would be failing the class? Well, if there's 24 over the year, there's 12 months, on average, it would be 2 a month. That's all we're doing here. That's all. We're just converting, like we have some average rate over a larger time, and we're just trying to convert it down to the interval that we want, which was a minute. Yep. And just to kind of complete, I guess, maybe this idea, talk a little bit more. Similar to the binomial with the Poisson, and I'm not saying we would have been able to really know that it was going to be 0.16, but if you think about what this probability should be, if on average, I'm only seeing 1/5 or 0.2, what are going to be my most likely outcomes? If on average, over a minute, I only see 0.2 emails, what are the most likely outcomes going to be? The values on either side of my mean. So 0 is going to be really likely, right? 0.2, right? I mean, 0 is going to be very likely for me to see. And then 1 is going to be like the second most likely outcome, but not quite as likely, right? Because 0.2 is a lot closer to 0 than it is to 1. I don't have any values on the left of 0 that are going to pull the mean down, but I do have some values to the right that even though they're not very likely, they'll still pull the mean up a little bit. And so we have kind of this distribution like that falls off very quickly when I have a really low lambda.